In curvilinear coordinate system, today we are going to find the expression for arc length and volume element. You will see in the forthcoming lecture that this concept of arc length and volume element is very useful, particularly when we will discuss the orthogonal curvilinear coordinate system and the transformation equations, that is the spherical polar coordinate system, cylindrical coordinate system, and the Cartesian coordinate system. So let us start with the concept which we have developed in the previous lectures, that you consider there is a point P in a space, and this point P is specified in terms of the curvilinear coordinates u1, u2 and u3. In this condition, you have seen we have a transformation equation for the position vector r of the point P. So you can say the position vector of a point P is given as, you have seen this transformation equation in the earlier lecture, that this r is given as r as a function of u1, u2 and u3, where you know u1, u2, u3 are the curvilinear coordinates of the point P. So if r is equal to r of u1, u2, u3, then you know what will be the elementary displacement dr. Since r is a function of three independent variables u1, u2 and u3, so we will find the value of dr in terms of the concept of partial differentiation. And so you know from this idea that this dr will be equal to del r by del u1 du1. When you write this first term, you keep u2 and u3 constant. Similarly, the second term will be del r by del u2 du2 and plus del r by del u3 du3. Now you have seen in the previous lecture that this vector del r by del u1, which is tangential to the u1 curve, this vector del r by del u1, we have seen in the earlier lecture that this is equal to h1 e1 hat. So this can be written as h1 du1 e1 hat. Similarly, del r by del u2, you have seen in the previous lecture that this is equal to h2 e2. So we can write it h2 du2 e2 hat. And the third term can be written as h3 du3 e3 hat. You know here h1, h2 and h3 are scale factors which we have discussed in the previous lecture. So let us say this is your equation 1. Now once you know the value of dr, you can easily find what will be the differential arc length. If the differential arc length is supposed to be ds, then the square of ds will be equal to a scalar product of dr with dr. So you can say the differential arc length is given as, given by this is given by ds square equal to dr dot dr. Now see, dr is equal to this much, and when you will take the scalar product of dr with dr, the similar term will be non-zero and all the dissimilar term vanishes in a scalar product. So this will be simply equal to h1 square du1 square plus h2 square du2 square and plus h3 square du3 square, because you know that ei dot ej is equal to 0, but ei dot ei is equal to 1, where I and j is equal to 1, 2 and 3. So this is your equation 2, let us say. Now for general curvilinear coordinates, when we will find this dr vector, this result actually holds for orthogonal coordinate system. This is for orthogonal curvilinear coordinates. Curvilinear coordinates, because in case of orthogonal curvilinear coordinates, ei dot ej is equal to 0. It means when I is not equal to j. In other words, you can say ei dot ej is equal to delta ij, where delta ij is Kronecker delta, and you know this is equal to 0 when I is not equal to j, and this is equal to 1 when I is equal to j. So if the coordinate system is orthogonal, then ds square will be equal to this much. But if we consider the general curvilinear coordinate system, where there is no needed to be the system should be orthogonal, then what will be ds square? We will find it. So for the general curvilinear coordinates, what will be this ds square? You can see this will be again dr dot dr, and as dr is equal to h1 du1 e1 hat plus h2 du2 e2 hat plus h3 du3 e3 hat dot again h1 du1 e1 hat plus h2 du2 e2 hat plus h3 du3 e3 hat. Now let us take the scalar product of these two vectors. You will see this can be written as but first of all we should express this vectors in this form, and after that we will find this result in case of the general or curvilinear coordinate system. So let us first of all see what will be the expression for dr in case of general curvilinear coordinate system. So for general curvilinear coordinate system, you may define this dr vector like this. This is alpha 1 du1 plus alpha 2 du2 plus alpha 3 du3. We can define this dr in this manner in case of general curvilinear coordinate system. And so in this case, ds square will be equal to dr dot dr, and when you will take the scalar product of this vector with itself, what will be your result? You can see easily. This will be in fact alpha 1 dot alpha 1 du1 square plus alpha 1 dot alpha 2 du1 du2 plus alpha 1 dot alpha 3 du1 du3, and plus when you will take the scalar product with alpha 2 du2 of all terms, then the result will be alpha 2 dot alpha 1 du2 du1 plus alpha 2 dot alpha 2 du2 square plus alpha 2 dot alpha 3 du2 du3 plus alpha 3 dot alpha 1 du3 du1 plus alpha 3 dot alpha 2 du3 du2, and plus finally alpha 3 dot alpha 3 du3 square. You can see in compact form the expression in RHS of this equation can be written in terms of the sign of summation. We take the double sign of summation for two variables. Let us say this first variable is p, which runs from 1 to 3, and another is q, which also runs from 1 to 3. And then you can write gpq dup duq, and this is your equation 3. Let us say, in fact here I have written this gpq is equal to alpha p dot alpha q, where p and q both runs from 1 to 3. Actually, this quantity gpq is known as the fundamental quadratic form or metric form. Actually, in the previous lecture you have seen already this quantity, this metric gpq. So you can say that this quantity gpq is known as fundamental quadratic form or metric form. This is called the fundamental quadratic form or metric form. Actually, these quantities GPQ are also called metric coefficient, and this is just actually a symmetric covariant tensor. So you can say these are also called metric coefficient. And you have already seen this in the previous lecture. Now, as we know that alpha p dot alpha q is equal to alpha q dot alpha p, because a scalar product of two vectors is actually commutative. So this implies that GPQ is equal to GQP. And if GPQ is equal to GQP, it means these metric coefficients are symmetric. So this implies that these quantities are symmetric. Now, if you will consider that P is not equal to Q, if P is not equal to Q, then actually alpha P dot alpha Q is equal to 0, and therefore we can say that this GPQ is equal to 0. In fact, if this condition holds, that alpha P dot alpha Q is equal to 0 when P is not equal to Q, and then GPQ is 0, in fact this condition will hold when the coordinate system is orthogonal. So this condition implies orthogonal curvilinear coordinates. Orthogonal coordinates. But if this condition does not hold, then the curvilinear coordinate system are not orthogonal. But in fact, the concept of orthogonal coordinate system is more important, and particularly you can see in this condition, when you will consider the different values of P and Q, what will be the values of GPQ in case of orthogonal curvilinear coordinate system. So in case of orthogonal coordinates, you can see that this G11, this will be equal to H1 square. Similarly, G22, this will be equal to H2 square, and G33, this is equal to H3 square. This is a most important result which will be used invariably when you will discuss the forthcoming concepts regarding the curvilinear coordinate system. So remember it. Now you can see this figure. In fact, in this figure we have considered a volume element, and we have shown in this figure the vectors h1 du1 e1 hat, h2 du2 e2 hat, and h3 du3 e3 hat. Actually, these three vectors form the sides of a parallelepiped, and so we can find what will be the volume of this parallelepiped, which is actually called volume element. You know from the vector algebra how we can find this volume element. So according to the figure, the volume element of an in orthogonal curvilinear coordinate system, you can find it. So in orthogonal curvilinear coordinate system, system, the volume element is given as, this is just the geometrical meaning of cross product of vectors, and this can be given as h1 du1 e1 hat cross h2 du2 e2 hat dot h3 du3 e3 hat. Now, since the coordinate system is orthogonal, and you have seen in case of orthogonal curvilinear coordinate system, this e1 hat cross e2 hat will be equal to e3 hat. So this will be h1 h2 du1 du2, and e1 cross e2, this will be e3 hat, and dot h3 du3 e3 hat. So now e3 dot e3, this will be equal to 1. So you can write this is equal to h1 h2 h3 du1 du2 du3. So this is actually the expression for the volume element in case of the orthogonal curvilinear coordinate system. Remember, this result is not a general result. This will be valid only when your coordinate system is orthogonal. And you will see when we will discuss the particular orthogonal curvilinear coordinate system, then this result will be very useful. So this is all about the arc length and volume element in orthogonal curvilinear coordinate system. Now in the forthcoming lecture, we will see the orthogonality of this curvilinear coordinate system and the particular orthogonal curvilinear coordinate system.